memorize our unit circle, know values from that, and all of the coterminal ones, we can now solve equations without our calculator. So this would become a question that would show up on a non-calculator part. You would ask, can you solve sine theta equals negative root 3 over 2 between 0 and 2 pi? If this was in grade 11, you would have said, well, it would be between 0 and 360 degrees instead of 0 and 2 pi. In grade 11, you would have gone to your calculator and found your reference angle. You would have looked at your CAS rule and said sine is negative in quadrants 3 and quadrants 4. Drawn your triangles, found your reference angle, and then found your two angles in quadrant 3 and 4. So that's just a review of how we normally have solved trig questions from now. We would use our CAS rule to figure out what quadrants it's in. We'd find our reference angle, then use your reference angle to find the actual angle. Now that we have our unit circle, we would say, hey, I recognize root 3 over 2 is a coordinate on our unit circle. We're looking for, when is the y coordinate root 3 over 2? What family is that? Pi over 6, pi over 4, pi over 3, axis family. So you would think about your unit circle. And you would immediately say, I know that this is part of my pi over 3 family. Because if I think about my unit circle, when is the y coordinate root 3 over 2 in quadrant 1? That's my pi over 3 family. Once I know that my reference angle is pi over 3, the actual answer to this, because of our CAS rule, it can't be in quadrant 1 and 2 because sine is negative, so it needs to be in quadrant 3 or 4. What is your pi over 3 family in quadrant 3? 4 pi over 3. What is your pi over 3 family in quadrant 4? 5 pi over 3. So we save a lot of time because we don't need our calculator. Our reference angle is easy to find, and then we just have to think what quadrants it's in to write our final answer. So again, we always will have to check what's the domain, where are they asking for the answers. In this question, from 0 to 2 pi, we think about our unit circle. That is once around in the positive direction. When we look at a question that's non-calculator, we're basically asking, do these coordinates ever show up on our unit circle? Big idea, cos theta is x coordinate or y coordinate? Cos theta is our x coordinate. Is the x coordinate on here ever negative 1? Yes. And that's all we'll have to write for a question like this. So we're using our unit circle to determine where does this happen on our unit circle. It happens when the angle is pi. That's the only time that your x coordinate is negative 1. Is tan ever equal to 1? What family is that? So as soon as you figure out your family, you've figured out your reference angle. Then according to our CAS rule, tan is negative, so it's not in quadrant 1 or quadrant 3. It has to be in quadrant 2 and quadrant 4. So then we have to go to our unit circle and say, what is my pi over 4 family in quadrant 2? And maybe you use the strategy of the numerator is 1 less than the denominator for quadrant 2. So we got quadrant 2 would be 3 pi over 4. Quadrant 4, 7 pi over 4. So for certain questions, this makes solving trig equations super fast. Much faster than we had before. If you get one of the reciprocal functions, secant, cotangent, cosecant, the first thing you'll do is say if secant of theta is 2, then cos of theta is the reciprocal, 1 over 2. Next, we think about our pi plate. Cos is your x-coordinate. What family has an x-coordinate of a half? Once you figure out what family has an x-coordinate of a half, you have your reference angle. How do you do? How's your memory going? So in each of these, you should try to see if you can figure out the reference angle before I write it down. Pi over 3. Then according to your cast rule, we are looking for where cos is positive, so it's not here and not here. These are the two places it has to be positive. So now we need to write, what is my pi over 3 in quadrant 1? Well, that's easy, pi over 3. What is my pi over 3 in quadrant 4? 5 pi over 3. Okay, try this one first on your own. Once you're done, you can check up here to see if you were able to get it right. So with the unit circle, we will now have all of these questions that we had in the past for trigonometry. If we can do them without our calculator, we will, but we will still be required for anything that's not on our pi plate to do them with our calculator. So you're going to have to be able to recognize when values are from your pi plate and when you have to use your calculator. The easiest way to tell on a test if something is probably from your pi plate is when it shows up on the non-calculator part of your test. You're like, oh, it must be from my pi plate because it's on the non-calculator part. We also combine all of your skills from factoring from grade 11 and solving quadratic equations from grade 11 with our trig functions. So a little review of grade 11. In grade 11, you would have a question that looked like this. X squared minus x equals 0, and you had to factor to solve. In this type of factoring was noticing that both terms have something in common, and I can factor out that x because it's in common, leaving me with either x is 0 or x is equal to 1. A little bit of a reason why we factor and why it's so powerful. Because it's sometimes if you know why you do something, it kind of like, okay, that makes sense. I can appreciate it more when I know why it works, rather than I just do something and you don't appreciate it. So in mathematics, if you are subtracting two things, as we have at the beginning here, right? I'm subtracting two things and they equal 0. I can put two numbers in my head and subtract them, and they equal 0. And I bet you could guess for a very long time before you guessed right. What two numbers do I have in my head? Any guess? Subtracting two numbers, they're equal to 0. Pick a guess. Pick any. I have two numbers in my head. I am subtracting them, and they equal 0. You just have to guess what one of the numbers is. No. Take a guess.
3.
3, no.
2.
Bill.
7.
Oh, no.
I was catching.
I have two numbers in my head. I'm subtracting them. One number minus another number. You just have to guess what one of the numbers is. See if you're right.
11.
No. How long could we go on? The number was, one number was 7.2 minus 7.2. You're like, that's not fair. I used to guess. How long would it take you before you guessed that right? We could probably spend the next week guessing. You'd be really happy. What are you doing in math today? We're guessing. And we're getting it wrong every single time. It would take a long time. Now, the powerful thing about factoring is right here. You change something that is, in this case, subtracting. Factoring changes it to multiplying. I'm going to get two new numbers in my head. You just have to guess one of them. Okay, I've got it. I multiply the two numbers together, and it's equal to 0. What's one of the numbers? You can see that one of them has to be 0. The other one was 3.79. But one of them has to be 0. This is why factoring is so powerful, because as soon as you factor it, you know that either this one is 0 or this one is 0. That has to be true. The only way you can multiply two things and get 0 is if one of them is 0. And that's how we solve. We say, well, if the green one is 0, then x would be 0. If what I circled in red is 0, then x would have to be 1. And now we've solved the original equation with the only things that work to do that. The only number squared minus another number that equals 0 is if either x is 1, because 1 squared minus 1 works, or if x is 0. That's the power of factoring. That's a review of grade 11. So we will use all of our factoring skills in grade 11, because whenever we have a quadratic equation, and a quadratic equation is when you have something squared. This is a quadratic equation because we have a co-squared. So just like we did with our x's, we would say there's a common factor of cos. There's a cos theta in both the first term and the second term. I can factor that out. And by factoring it, I've changed it to multiplication. So now my multiplication is right here. I have two things multiplied to equal 0. Either the first one is 0, in which case cos of theta would be 0, or the second one is 0, in which case cos of theta would have to be positive 1 for that second set of brackets to equal 0. We haven't solved for theta yet, but now, hey, this is our axis family. When is your x coordinate 0? How did you do? Your x coordinate is 0 at pi over 2 and 3 pi over 2. When is your x coordinate 1? At 0. Also at 2 pi. And here we have to be really careful, because I'm going to tell you, sometimes the textbook will see if you're paying attention to details. They will give this same question, and they will write this at the top. see how similar that is to what we had? Only one tiny little line is missing. What was written for us is theta is between 0 and 2 pi, but with the line it says include 0 and include 2 pi. So when we have cos theta equals 1, we would have to include the answer of 0 and we'd have to include the answer of 2 pi. If the question was written without that line, then you would not write 2 pi as an answer because the 2 pi is not included. So again, this course really pays attention to detail. You will want to, once you're done a question, read the question again, look at the details, ask yourself, did I pay attention to all of the details as I went along? Okay, so there's question A. That was factoring from grade 11 with a common factor. Part B. How do you solve something when there's just something squared? Like if you had x squared minus 5, what would you do if you had to solve for x? Okay. Would you move the 5 over and square root both sides? Perfect. Right? If you have just something squared, you can solve it. You don't need factoring. You just solve it by square rooting both sides. And what do you have to remember when you square root both sides of an equation? You have to remember plus or minus 5. So now we have a trig function that's squared, and that's the only thing that's squared. I can get it by itself. And I can square root both sides. When I square root both sides, it can be positive or negative, so I have to remember the plus or minus. And this question would be a non-calculator question. But right now, it doesn't look like something that's on our pie plate. We have to take the time to manipulate this equation, use our rules for square roots. Like the square root of a fraction is the same as the square root of the top over the square root of the bottom. And then I hope that you notice it's like, oh, I know the square root of 4. The square root of 4 would just be a 2. Then all of a sudden you're like, root 3 over 2? Is that on my pie plate? Yes. Sine is my y coordinate. What family has root 3 over 2 as the y coordinate? Pi over 3 family. And according to your cast rule, do you see that you're looking in all 4 quadrants? Because we have positive root 3 over 2 and negative root 3 over 2. So we have to list every single pi over 3 family member. All 4 answers would show up. So off to the side is doing the review of grade 11, right? Grade 12, we have trig functions. Grade 11, you just had x's. If you had a quadratic equation like this, and you had to solve it, you had 2 options. You could factor, or you could use a quadratic formula. Right? If you're feeling like your factoring skills aren't very good, or you're getting stuck on something, use your quadratic formula, right? Ideally, we want to be able to factor things quickly because we will factor, just like you factored a lot in grade 11, you're going to factor a lot in grade 12. So if you're not good at factoring yet, you need to start to get good at factoring and start to think about what does it mean to factor something, okay? Now, in grade 12, for the most part, when you go to factor something, I want you to be able to do it directly. So you write the equation right underneath, we're going to want to factor. And there are a couple of strategies that I'd like you to use for factoring. First of all, when you multiply something out, the first ones here will always multiply to give you your first number there. The last ones will always multiply to give you your last number there. It's really important that you know the connection between multiplying out and factoring. Because as soon as you factor, it is my expectation every single time that you multiply it out in your head to double check that you have factored correctly. And sometimes, if you're stuck and can't factor, I would argue that a good strategy for factoring is to make something work for the first ones, make something work for the last ones, and try it and see where you go wrong. Actually getting a wrong answer and checking it can be a great strategy for helping you find the right answer. So, for factoring this one, if my first number is a 2x squared, there's actually only one possibility for my first numbers. Using nice numbers, the only possibility would be 2x and x. Can you see that? There's no other way to get 2 other than 1 times 2. Unless you go to fractions, but for factoring, factoring doesn't involve fractions, it's always whole numbers. At least not the factoring we do. Factoring we do will always have whole numbers. So, if this is a 2x squared, my only possibility is 2x and x. Then I go to my last number. It has to be a 1. That one is probably the easiest one that exists. It has to be 1 and 1. And finally, when we're multiplying this out, we have to decide, are they going to be plus 1s or minus 1s? Well, in order to get a plus 1, they either both have to be positive or both have to be negative. And we need, when we multiply this out, so remember how to multiply this out. You multiply this one, you multiply this one, you multiply this one, and you multiply this one. Right? In English classes, did your teacher ever use the word FOIL? Multiply the first ones, the outside ones, the inside ones, the last ones. So if you remember that, that's just telling you that all of the arrows have to happen. So when checking this, do my first ones make 2x squared? Yes. Do my last ones make a 1? Well, I'm going to have to check that because it's either going to be both positive or both negative. But I need my outside, which is 2x, and my inside, which is 1x, to combine to give me negative 3x. Well, I see that negative 3x. That would mean my outside would need to be negative 2x, my inside negative 1x to make negative 3x. Factoring involves a lot of mental math all at the same time. You're going to be multiplying 2 things and then multiplying another 2 and adding them together so we can factor this. And we have to get good at doing this really quickly. So since this factors to 2x minus 1, x minus 1, now you've changed it from adding and subtracting to multiplying. So in grade 11, you could split it here and say, well, if the first one is 0, then x would be 1/2. If the second one is 0, then x would be 1. In grade 12, in trigonometry, now we're doing the same thing. Except to get 2 sine squared, the only possibility would be 2 sine theta and sine theta. To get 1, our possibility is 1 and 1. And we need our outside and our inside to make negative 3. So the outside will be negative 2, inside will be negative 1. This gives me negative 3. Splitting this up. If this one's 0, then sine of theta is 1/2. If this one's 0, then sine of theta is 1. What family has a y-coordinate of a half? A reference angle would be pi over 6. What quadrants am I looking in? Quadrant 1 and quadrant 2. When is my y-coordinate equal to 1? That's an axis family. That happens at pi over 2. We will get questions that are solving trig equations, that are quadratic equations like this one. But now, what makes this difficult is you have cos and you have sine. You can only factor if you have the same variable. And these questions will require that you use the big idea. We'll learn later that these are called identities. One of our big ideas from this unit is that sine squared theta plus cos squared theta is equal to 1. From this big idea, you can rearrange this either to get sine squared by itself. Can you see that if I subtract cos squared on both sides? Or you can rearrange it to get cos squared by itself if you subtract sine squared on both sides. And what this allows us to do is take our original equation, which was negative 3 sine theta minus, now I'm going to put a big set of brackets, minus 3 equals 0. Can you notice that I rewrote the equation, but I didn't write one thing. The one thing I didn't write was cos squared. The big idea lets me rearrange this and say, I can replace cos squared because it's equal to 1 minus sine squared. I can replace it. I'll even do it in Greek. I replace the cos squared with a 1 minus sine squared. I had to do this because my original equation had 2 trig functions, and that makes it not able to factor. If we can change everything to having only 1 trig function, maybe we can factor and solve. So, what do we get? If I distribute my negative, I'm going to get a positive sine squared. I still have minus 3 sine theta. Minus 1 minus 3 will give me minus 4 equals 0. We have a quadratic equation. We're going to see if we can factor it. If it's factorable, the first one is sine squared. The only possibility would be sine theta and sine theta. The last number is 4. Now you have more than one option. So for factoring, this is where the mental math comes into play. You have to think, should it be 2 and 2 or 4 and 1? And while thinking about that, you know that your outside and your inside combined have to give you minus 3. So if you tried 2 and 2, can you see that the outside would be 2 sine theta, the inside would be 2 sine theta? That would not give you minus 3. But if you tried 4 and 1, now my inside is 4, my outside is 1. I need to get a negative 3. So I'm going to make negative 4 plus 1. Because negative 4 sine theta plus 1 sine theta would give me negative 3 sine theta. Once I've got that written down, I do a complete multiplication in my head to check. Does sine times sine give me sine squared? Yes. My outside and inside, just check that. That gave me minus 3. Do my last ones, minus 4 times plus 1, give me minus 4? Yes. So now we split it here. If it's equal to 0, then either sine theta equals 4, that would make the first factor equal to 0, or sine theta could be minus 1, that would make your second factor equal to 0. Of those two values, only one of them is on your unit circle. Minus 1 is on your unit circle. You ask yourself, when is my y-coordinate minus 1? That's here at the bottom at 3 pi over 2. This is still going to be, normally if they're not on your unit circle, you would need to use your calculator and find a quadrant it's in, find your reference angle, and solve using your reference angle. So just the way that we've always solved trig equations in the past. This, however, is a non-calculator question all the way through, even though 4 is not on your unit circle. And the reason for that is because if sine is opposite over hypotenuse, and I make 4 a fraction, can you draw me a triangle where the opposite side is 4 and the hypotenuse is 1? No. So we can do this without our calculator because we can say that side is not possible because it's impossible to draw a right angled triangle where the opposite side is 4 and the hypotenuse is 1. In other words, anytime, and this is true for sine and for cos, not for tangent, but anytime for sine or cos, if you get an answer that's bigger than 1, you'll be able to right away just say, it's not possible because I can't have opposite over hypotenuse bigger than 1. All right, one more to go. Maybe 2. Maybe I'll add an F. You see a quadratic equation. Step 1 for solving quadratics from grade 11. Always need to make one side equal to 0, because if we can factor this, then it needs to be equal to 0 so that we can use that idea of 2 things multiplied by 0. One of them has to be 0. So solving any quadratic equation, you're going to want to make one side equal to 0. If we go to factor this, okay? This is harder to factor because when students like to write the first ones first, because you're logical, straightforward people, you like to write the first ones first. What's hard in this one is your first one being a 6 sine squared, you have more than one option. It could be 6 sine and sine, or 2 sine and 3 sine. So some students just say, I'm going to guess one of them and see how it goes. If it doesn't work, I'm going to guess the other one and see how it goes. Okay? Now, I would say in this question, since I don't know what to start with 6, I look at my other number. My last number is a 1. That I can do. The only possibility to get 1 would be 1 and 1. So I would actually start with my last one here. And now, I have something to work with when I think about, right, my outside and my inside have to make 1 sine theta. I hope you can see that if you use 6 and 1, the outside would be 6, the inside would be 1, there's no way you're getting plus 1, adding or subtracting. But if you use 3 and 2, my outside is 3 sine theta, my inside is 2 sine theta. If I subtract, that would get me 1. So I would need a positive 3 sine theta minus 2 sine theta to get 1 sine theta. I quickly check, multiply this all out. My last one works to -1. My first ones work to 6 sine squared. Outside and inside work as well. So now I can split it here, and I get sine of theta is 1/3. And sine of theta is -1/2. The 1/2 is on your unit circle. That's your pi over 6 diamond. So we can tell without our calculator, it has to be in quadrant 3 and quadrant 4 because sine is negative according to your cast rule. And you get 7 pi over 6 and 11 pi over 6. For 1/3, that is not on our pi plate. So here, we are going to be required to go to our calculator. We're going to think about our cast rule and say, I know that it's in either quadrant 1 or quadrant 2 because sine is positive. I can draw back to my x-axis, and both of those would have a reference angle. What do I know about those triangles? That the opposite side is 1, the hypotenuse is 3. And I can solve for my reference angle because those are regular triangles. I can have sine of my reference angle is 1/3. Going to my calculator, doing sine inverse of 1/3 in radians, so we make sure our calculator is in radians. I get 0.34. Then my answer for theta, well, in quadrant 1, it would be 0.34, the same as my reference angle. In quadrant 2, I would be figuring out this angle theta right here. In degrees, I would do 180 minus my reference angle. In radians, I would do pi minus my reference angle. Go to my calculator and get 2.80. So part E here would be a question that would be on a calculator part of your test. They would expect you to do the right-hand side as exact answers if you can. So the 7 pi over 6 and 11 pi over 6, you would be expected to get exact answers because they're from your unit circle. But the 1/3, you would have to go back and do the same strategy that you've done all the way along, finding a reference angle, thinking about your cast rule, and stating the two answers that way. I am going to give you one more, because we haven't done one with the quadratic formula yet. We'll do one question that involves a quadratic formula. Quadratic formula is on your formula sheet. On your formula sheet, you would have your quadratic formula. And again, you can use your quadratic formula even if you can factor it, but you're getting stuck on the factoring, you can go to your quadratic formula. This one that I gave you cannot be factored. If you tried to factor it, everything you would try doesn't work until you've exhausted every possible option, and you have to conclude this can't be factored. So then we would need to go to the quadratic formula. Now the quadratic formula on your formula sheet says for 8x squared plus bx plus c equals 0, and we don't have an x squared, we have tan squared. So the quadratic formula is usually x equals, but in our situation, it will be tan x equals negative b. So the b value is what's in front of the second one, that's a 1, plus or minus b squared, which will be 1, minus 4, a value would be 1, c value negative 7, over 2 times a. So we get tan of x equals negative 1 plus or minus the square root of 29 over 2. The plus or minus really means that there are two options, and I'm going to write them out separately. One option is with the plus sign. The other option is with the minus sign. And we'll do, both of these have to be solved separately. First of all, you might want to take tan of x here and just change this to a decimal. This is good practice for your calculator. Make sure that you can type this into your calculator correctly. You might want to try it on your own to see if you were able to get 2.19258 ... We could do the same thing on the other side. And you get negative 3.192. If you had to use the quadratic formula, most likely these are not on your pie plate. So we have to go through and say, okay, according to my cast rule, tan is positive in quadrant 1 and quadrant 3. Draw a triangle, label my reference angle. I would know that tan is opposite over adjacent, so I could label that this is 2.192 over 1. I could find my reference angle by doing tan inverse of 2.192, and I get my reference angle to be 1.14. I can now find my actual angle x to be, well, in quadrant 1, it'll be the same as my reference angle. In quadrant 2, I would have to do pi plus my reference angle, 4.28. I have to do the same thing on the other side, but this time tan is negative, so it's either in quadrant 2 or quadrant 4. These are my reference angles. And if your angle is x, you should use x with a little r. If your angle's theta, theta with a little r. There are my reference angles. If you want to find your reference angle, you're going to do tan inverse, but you're always doing tan inverse of a positive value. Reference angles are based on actual triangles with actual lengths. So when we do tan inverse here, we have to do tan inverse of positive 3.192. Your reference angle is 1.27. So in quadrant 2, you would do pi minus your reference angle. in quadrant 4, 2 pi minus your reference angle.